Wait, can the mass in this Diagnose cookie be the same mass used to diagnose cancer?
The answer is yes. And to understand why, let's crack open this cookie.
Look, here's a line crack, but something looks suspicious. It's actually a circle in disguise. Zoom in and the curve looks like a straight line. However, this cookie on the right is a Sierpinski triangle. When you zoom in, it never straightens. Instead, more and more details keep appearing. Structures like these are called fractals, patterns that reveal infinite complexity the closer that you look. Notably, each time you zoom in on the Sierpinski triangle, it looks like a smaller version of the whole. This property is called self-similarity, and in mathematics, we often see deterministic fractals with perfectly precise self-similarity, while in nature, fractals tend to be statistical, meaning they show randomness at each scale of repeated patterns. But here's the real challenge. How do we measure a fractal's complexity?
Let's go to the baking sheet.
With a box that has a side length of s equals 1, we only need one box to cover this fractal. Now shrink the boxes. When s equals 1/2, we need 3 boxes. Keep dividing and a pattern forms. Plug in values and solve for d, you get 1.585. D is a fractal dimension, aka how wiggly a fractal is, measured with a box counting method.
And nature is all about that wiggle. By measuring the tiny changes in fractal dimensions, doctors can differentiate between different stages of cancer, and this raises exciting possibilities for fractal-based method in cancer detection. This all goes to show that big breakthroughs can start with small cracks, even in a Diagnose cookie.